Okay, guys, now we have the motion of a charged particle through a uniform magnetic field. And this one's pretty straightforward. Um, so here's our formula for the force on a charged particle. But let's see, here's our magnetic field, and it's going into the page again. Okay, it's a big magnetic field, and it goes on forever, or at least it seems like that for the particle itself. And we get a particle that enters the magnetic field. Okay, it's entered the magnetic field. It's got a plus charge, and here is there's its velocity. Well, when it experiences this, so it's got it's going that way, and then we're going to curl that into the page, and it's going to make our force vector on this thing go in the j-hat direction. Okay, so if we have, so let's review we'll have v is our velocity here is I hat, up is j hat, and up and down. So this is negative k hat, right? So I cross negative k is going to give us j, or k cross I gives us j, also gives us j. Our force is going to be in this direction, which means that as it moves, it's going to have a new velocity in a moment that's going to be in that direction. And so the force on that is going to be here. And then it's going to move again and so the force on this is going to be here. And what's going to happen is, well, this creates you can sort of see what's happening, that if we have a force acting perpendicular to our velocity, then that creates a motion I wish those weren't parallel, but looks like they'll meet about here. This creates a motion that will cause this to go in a circle through the field, so long as it maintains the velocity. And there's nothing slowing it down. So if there is nothing slowing it down, it will eventually do, and I realize that's a really crappy circle, but that is intended to be a circle as it goes around as our particles experience the force, okay, perpendicular to their motion and perpendicular to the field. All right, so let's do a little bit of math on this. That means we're going to have our force equals q v cross b. But what kind of a force is this? Well, if it's a force that's traveling towards the center of a circle, this is centripetal force. Okay, and so it is given by this. So it's mv squared over r in the negative r hat direction. All right, so since we can tell that it's always in that direction, we'll drop our vectors here, and we're going to get q v, drop the vectors, vb equals mv squared over r. Okay, our v can cancel with one of those v's, and so we have a number of things that we can find with this. We can find the radius of curvature, okay, where the radius is going to equal mv over our charge times the field, and this is going to be important here in a little bit. If you look at this is the momentum of the particle divided by the charge of the particle times the magnetic field. Well, a lot of times we can only determine the momentum of the particle. We can't find its mass or its volume in particular, and that's why this is so important when we're dealing with subatomic particles that have charges passing through a magnetic field. Or we can solve for v over r. Okay, if we solve for v over r, this is how fast it's going divided by the radius, which really winds up being Okay, our angular frequency, because it's how many radians per second it's going to be traveling. Okay, and that's going to wind up being QB over the mass. Okay, and this omega right here is called the cyclotron frequency. Okay, is this many radians per second, and it's QB over m, so it's going to be our charge of the particle times the magnetic field divided by the mass, and that's how we can tell how many radians per second it's going to travel. So if it's going really fast, then it's independent of the actual size of the circle. Is the cyclotron frequency. This radius and the velocity kind of work together to eliminate the idea of the concept of the size of the circle. Okay, and that's how we can standardize across all of the cyclotrons. So go from Fermilab to the Large Hadron Collider to a number of different actual cyclotrons, and their results should be the same. Because they should be able to travel. If the radius is going to increase, then they should be able to move something at a higher velocity and maintain the same cyclotron frequency, which is really a function of the charge times the magnetic field over the mass of the particle. And this is an oversimplification, but this is what they needed to use to find the Higgs boson, which, of course, as with any new science, they're still squabbling over and say, yes, we found it. No, you didn't find it. Yes, we found it. No, we found it, and that sort of stuff. Okay, so I want you to think of another situation here. That we've got. Okay, so I'm going to draw, and I'm going to bust out with another color here and make a giant axis here. Now we've got a Y. That's our J-hat axis. That's our Y-hat axis. Here's our K-hat. All right, and imagine we have a particle that, and here's our magnetic field is, not only is it just this way, but it is also filling up the space. Okay, so it's throughout, this whole thing has a magnetic field going through it. And so we start with a particle that is down in here somewhere. What is this? Okay, and it travels in a direction that is out like this. Okay, away from the origin. Okay, not parallel to the field, but away from the origin. What's going to happen? Well, it has two vectors with it. So if our magnetic field is all in the I-hat direction, then the magnitudes of this that's what I should draw. So we're going to have a magnitude of our velocity in the K-hat direction, and we're going to have a magnitude of the velocity in the J-hat direction. And because we have magnitudes of the velocities in both of those directions, we're also going to have forces that are perpendicular to those guys. And that actually causes the path of this charged particle. Okay, I'm going to violate my color coding here. It's going to cause the path of this charged particle to spiral. Because the forces as this thing is moving are going to be changing into and out of each of the perpendicular directions. And so we get this. Okay, so it's not really a spiral, it is a circle that is changing. So the forces are let's look on this end on, that the particle is coming out at us like this. This is the direction of the particle. Well, because it's going to experience a force in that direction and then that direction, or it's going to be back and forth depending on how it's moving, okay, that this particle is going to travel in this circle like this if we are looking at it from end on. In fact, let me draw a better picture. It's going to travel in a circle. If this is the vector, it's going to travel in a circle that looks like this, and it's going to go around and around, around and around and around, okay, as time goes. But if that's just if we're looking at it end on end. But if we're looking at it as if we're looking at it from the side, okay, it's still traveling with a velocity going in this direction. So let's change this into the page vector and let's alter it to the side. And when we do that, it looks like this. Okay, because a circle, if you travel in a circle with respect to time, you start traveling with this spiraled path. And when it hits a bubble chamber and you see the curls, that's really what's happening, is these things spiraling through our bubble chamber. In fact, you'll see some of them that kind of look like that, and that's because their path through the bubble chamber, their path was in the plane of the bubble chamber, or a large part of it was in the path of the bubble chamber, and so we get this spiraling through our magnetic field because the component of the velocity that's in the direction of the magnetic field doesn't change, and so it travels in a straight line through there. But as you travel in a straight line, but the other ones are changing alternately, then you start getting this sphere, not sphere, this circular spiral-looking thing. So this is, and it'll spiral around the I-hat direction. And this is how charged particles move in a magnetic field.